So I want to show you a case which we have done in the past. So it's a cement plant in Europe. Unfortunately, I can't tell you any details about it. It has a 4,500 tons per day clinker production, and it's a so-called semi-dry system. And yeah, the calciners are two-stage calciners where we have, this is just the end of the rotary kiln, and we'll look at the calciners, and they have some operational issues. So they have what they call pumping. So it's a frequent change of pressure during operation, which may be caused by material fall out into the tertiary air duct knee, but they weren't very convinced about that or not sure about it if this is really the cause. They also have coatings and blockages in the bottom stage cyclones. So this means that they have a carryover of fuel and have afterburns in the cyclone. This is something you don't want to see here. And they also have CO limit exceptions, which is the most severe topic on this study. So the question is how to address this. Do you want to try it? And this is how it was done in the past quite frequently. So a lot of engineers with a lot of experience just know that from plant A it works, so it has to work for plant B. And as you mentioned in your talk, this is not working. If you have the same design, the same properties, it works still differently. This is true for the petrochemical industry, but also for the cement industry. So you have to be very specific on what you are looking at, and that's why we chose a model-based approach here. So for the model, we require quite deep insight into the calciner, so we have to look at a two-phase flow because the solids loading in the calciner is rather high, so we have to take this into account. We also have to consider the combustion to have the necessary energy, to have the necessary the correct temperatures and gas distribution, and we also have to have the proper velocities, otherwise we will not be able to achieve the right answers. And for that we have to also consider the chemical reaction about the calcination, because it's not only endothermic, but it's always reduces the volume of the gas. And since we want to look at the emissions of CO, we have to consider that also. So we also have to consider different fuels. So as I mentioned, secondary fuels are used, but how to characterize this. So there are a lot of questions about drag and how to model that, and we need some verifications for this lumpy fuel or rubber band. This will behave completely different from a sphere. So we have to consider that. So we actually built this so-called zig-zag sifter in an experiment, and we can introduce particles at the top and let them fall through this zigzag, and we have countercurrent airflow, and we take these experimental data and fit the model of Barracuda to it. And then we can use these settings to model the calciner. But also we have to consider particle shape, and since we also have quite large particles, fuel particles, we also have to consider a thermal shell model for these coarse particles, because assuming that the temperature is the same within the particle for these large model is not giving the right answers. So we have implemented thermal shell, so only the outer shell of the particle reaches the temperatures within the calciner and also is considered for the reaction. And we also have to look at the moisture distribution between within the particle? Is it only on the surface, or is it homogeneously distributed within the particle? So this is some process details. I don't want to go into detail about this, but when we look at the first simulation results, we see that we have some meal storage. What is given here is the particle mass within the calciner over time. So you see this is a typical load phase, but then we have quite severe fluctuations. So these are up to 400 kilograms within some seconds, and this is what they see as pumping and fluctuation of pressure. So the result is what the operators see is pressure fluctuations, but also fluctuations in flue gas composition. So this means that we have not only insufficient pneumatic conveying within the calciner, but we also have a maldistribution, which means that the reaction doesn't take place or evenly of the cross section. So this is one topic, and we can, if we want to look at the reactions, we have the oxygen concentration on the left-hand side, and here is an isovolume of CO-rich regions. So this is explaining not only the pumping, you can see how it's fluctuating down here, but also you have a mild distribution about the cross section. And as the calciner is just up to here, everything which is carried over here for CO means that we have unburned fuel, and we still have combustion within the cyclone, which leads to coating and build up of layers you certainly don't want to have. So this is also caused by poor pneumatic conveying. So for the optimization, we had a lot of different opportunities or possibilities, but I want to show you just some simple ones. We had introduced a steeper cone, and steeper cone combined with a slimmer shaft, so to raise the velocities, which on the one side reduces the time that is available within the calciner, but also reduces the pumping. So you have a more stable pneumatic conveying at the bottom. And to increase the time available, we also had an elongation of the calciner shaft and introduced a mixing chamber at the top. So from the operational view, this may sound as the most promising, but we also know that this is the most expensive revamp which has been done. This is why we try several different options. So here you can see the current scenario. The particles are colored by their species, so you can see how it is not very well mixed, and every now and then we have particles that fall through. And in the retrofit scenario, it's a much smoother operation. Of course, we have a longer time to have all the calcination done, and we also have no combustion afterwards. So what I like most about the study is that it is not only a study, it was really built, so it was realized by the third party, and after detail engineering and commissioning, they had the rebuild, and after that, we see that all process issues were eliminated. So this plant is now running with the redesigned calciner for about 2 years. We could increase the capacity. Now the secondary fuel rate is at 100%. So this is one goal, and we still match the CO emission. So this is really a success story, and it was done. All the engineering was done up front, so there were no trial and error, and the duration of the stop was just 6 weeks. So this is a rather typical stop during summertime, where they do typically the revamping. So this is quite obvious that CFD really helps here to not trial and error at the field, but just virtually.